stream or record. Okay, so what we are doing, we are using, for the laboratories, we are using PSoC 1 evaluation kit from Cyprus. On Metropolia, you can get it from me. On Frankfurt, you can get it from the lab engineer Robert Mikalik tomorrow. Or if you are somewhere else, then you can actually buy it, for example, from Cyprus Semiconductor website, or some other dealers. They're quite popular, actually. Okay, so basically what we are going to do today, we are going, or I am going through some tips how to actually work on the this environment, programming environment, and you should be actually doing the exercise 1. There's a link on the web page to the template. Okay, so the template was down on the sensors chapter, exercise 1, programmable system on chip fundamentals. But before starting to work on that environment, let's take a look at what I want you to return to me and how to return. Basically, when you are done with your today's exercise, you will click that return form, and yes, there are some places to fill. Okay, email address, any working email address will do. This is for your own good, since actually then you can also have a copy of your return yourself. I think it was also there, maybe. Did I click that one? But anyways, so basically I want to have a correspondence address just in case, since sometimes I get a nameless returns. Yep, and with the nickname on this form. So I really need to know who returned that sheet or returned the exercise in order to give you any points. So that's why there are required fields. Then also, of course, click on the exercise number, 1 to something. Those might actually change a bit. Then 2 links. One link is link to the report, and actually that report is the compressed compressed project files. So you take the project directory of that design tool, compress it, put it somewhere, I don't care, anywhere which gives a link to the compressed file. Dropbox will do, Microsoft Cloud will do, Google Cloud will do, as long as I can open it. Okay, that's the first place to check that it's anyone who has the link can open that, whatever you have on behind. Okay, preferably on those, use the tools that Metropolia provides you. So either Metropolia provided the Google or Microsoft Cloud. It's up to you to decide which one. They work exactly the same for this purpose. Okay, so that'll be the link. And as I told you earlier, if the link does not open, then I cannot give you a grade other than -1. And next time when it can be opened, that will be on the bottom. So if you otherwise would get 10 points, you will get 9 points because of that. Then you can actually, there's another one, there's good point also to lose 2 points. So it's also, you need to return the link to the main code, main function. I noticed that one actually very useful for the students, since mostly the coding on especially math systems and that kind of things, it's usually when it works it's done. Okay, not quite. There's supposed to be also some documentation what the code does, that kind of things. And also if there is a small error and you cannot get your exercise done completely, you can still earn the points by returning those, and I will give you feedback if I find the error on your main code. Okay, so that's basically you're doing a service to yourself when you're providing the main code. All right, so links, and there only reasonable way to give a link for the main code, what I have found now, so that I can actually give you some feedback, would be Google Documents. Okay, we could actually also have GitHubs and that kind of things, but then it requires some setup to get, you know, those setups there, so that actually anyone can give feedback to anyone and that kind of thing. So it's too much of maintenance. So preferably Google Docs, so that I can actually comment that document. But I will show you an example at some point. But anyways, that's the only way you can submit your exercise. If you have trouble submitting exercise, well, then you can email me that you couldn't for some reason. It should open actually. If this one opens, then it should be, you know, fillable. Okay. So that's how you return the exercises. And today we're going through the first one, which is the PSoC basics. There are some tasks, 1, 2, 3, 4, I think, and then exercise report return. And it says here it's a PSoC project files zipped, shared as a link. If everyone was in Metropolia and used Metropolia accounts, then we could actually have the share it as a package to somewhere, but otherwise now the sizes of the return form file sizes are limited, and there are some things like you cannot send a or return a file anywhere except from Metropolia Google form or Google account using those Google forms if you are returning files. So that's why there's a link. So zip and shared as a link. Okay, and it says all program files your own, meaning especially the main.c must be documented appropriately, and there's a minimum requirement. Each file starts with a commented area with description, author, date, and course ID. That's the minimum. And then fundamental principle that anyone with some programming language knowledge can be reading the code and think and know what it actually does. So understanding. So you're doing documentation to somebody else, a colleague of yours, but anyways, what happens? 1 year from now you would remember, oh, I did that exercise in that course. There's a funny teacher, and then you go to your own code. If you didn't document it, you would say, who wrote that one? And you know, the undocumented code is single-use code. It's not worth of actually doing even that one. So make it as a habit. Make the this at least the minimum requirement part of the documentation to your code. And another than there's a hint, use descriptive names for all added modules and user-defined signal pins and also the variables on your code. X and Y are extremely bad variable names, unless you are working on an XY printer or something like that. Okay. And zip it, upload it, create a link, and so on. Provide link also to main.c file for feedback. Okay, maybe I should actually highlight that one. Shared as anyone can comment with those parameters. And that's very important. Okay. Otherwise, this exercise actually is quite simple. We first go and start a new project on PSoC, name it with a, say, appropriate name. Then we start looking for the what kind of tools there are, with what kind of views, interconnects. There are a couple of questions here. Those questions are only for you. So if you want to save this one, go to your favorite Google account and make your own personal copy. I don't care. Sharing is caring. You can make your own personal notes based on this template. And then basically we go through the application editor, building a project, and how to program the device and test it. The environment, so to speak. That's basically more or less my, you just follow my lead, you'll be okay. Then task 2, you need to add a LED, which I need to still get here, LED. And, oh, you know, we don't, this actually had the LEDs, yes, okay, good. LED, and well, that's the first thing usually with any microcontroller. The first demonstration is a blinking LED light. All right, so yeah, we are making a blinking LED light. Pin output, pin input. Okay, this is something that actually requires a little bit of, say, ability to read assembly. Not assembly code, but this goes into in category of hardware related things. So embedded systems are the main difference between embedded system and any general purpose computer is about how you actually interact with the hardware. On embedded systems, it's always hardware related. You need to basically be able to control the pins, I/O pins of the circuit. And one is how to get input. The task 2 was actually how to get a digital output. Blinking LED. After that, you can blink anything. You can actually build your own software for any serial line interfacing. So setting a data to serial line. Okay, pin input would be just, you know, reading the data what comes to the pin. And now, usually the writing to the port is generally easier than reading from a port. There are more things that you need to consider when you are reading a port input. That are you actually reading the input from the port, or are you actually reading the input from somewhere else? Okay, but this actually gives you an idea how to do the reading. Then the last of this first exercise is about debugging environment. Since we do not have the this kind of emulator environment, so this is a simple microcontroller with some certain properties, but we do not have a, for example, this emulating environment where you can make breakpoints to the code and just run into that one, and this kind of better, higher, or more advanced the tools. You usually have that kind of things, and especially if you have a bigger, say 32-bit controller, then you usually need to also run the code line by line and that kind of things. We don't have it on this one. We don't have. There was actually that sort of version, and we got even donation of 10 sets of those, but okay, I was the first one to burn the first of those emulators. And I thought, okay, well, shit happens. Maybe I did something wrong. Then my colleague, actually, Kimmo, burned another one. Then I blamed, you just couldn't do it. But then on my first week, 3 more actually burned on laboratory without any reason. Then I noticed, okay, this is piece of garbage, and we stopped using them for obvious reasons. That was the first version of in-circuit emulators for these chips from Cyprus. It wasn't good. Okay, I can sell them cheap. We still have a couple of those around. Yeah, non-fried. Yeah, non-fried versions are still available. Okay, but anyways, so our debugging environment is that we can actually print to the LCD port, and you started already. Good. So this box actually has also the LCD that plugs into only one place, which says LCD, and there's also the so if you want to humor yourself, you can do the first connection. Okay, now it's set up for the LCD. Okay, but anyways, let's go and take a look at the environment. And fundamentally, when you have done all the exercises to your one single project, then you are done. You compress the package, put it somewhere on the online that you can provide a link to anyone, and then basically take that main.c, make sure that you have all the required documentation there, and then share the link so that I can comment. Yes, you have a question?
Copy and paste the C code.
Yes, yes.
Completely
Ignoring anything that it says. Yes. Yeah, it looks like well, it's the best. It's still the best method. Okay. So the Microsoft actually, you could put the main.c as a Microsoft cloud, but the sharing it's not. It's a little bit cumbersome, in my opinion. In my opinion, not humble opinion, but my opinion. Okay, good. So, yeah, PSoC Designer. It has all sorts of stuff when you open it. Lots of things happening. This is the kind of trend in the modern tools. Like, how do you like the OMA? It's all kind of information everywhere, and not that one that you actually need, but anyways, it has a lot of information. Same thing here. The most important thing actually is on the left top corner, which is actually a good place to put it. Okay, so actually the recent projects. So when you are starting working with this one, you usually go to start a new project or use an existing project. Or you are looking for a device that fits into your application. Okay, and then they have excellent documentation on that right corner saying design support, like application notes. I have a couple of links for the application notes on the, for example, on the how to use SPI or how to use the I2C on programmable system chips. The code examples, design guides. Then also, okay, if you don't have the development kit, you can actually get into their web store to buy it, and so on and so on. And basically, since it requires your registration before you can get the code, then you can actually go into these webinars, blogs, follow the blogs. You can put there some questions to the Cypress representatives, and they actually are answering those pretty fast. So if you have some specific question that you cannot find an answer, then they might actually help you. Okay, and it's say rather say vivid community. There's just a couple of samples of the community. When you log into it, like log into your account on Cypress, then you can see the community discussion groups and that kind of things. Okay, a left low corner, especially for those who are learning themselves how to create your first project, how to create a new project, and that kind of things. They are actually there. I think they're YouTube videos and that kind of stuff. Good instructions. So this is also self-learning material. That's the way I learned to use these. Okay, but anyways, so it starts like that. At the middle, they have these PSoC links. Great. so the middle of the tool is for a note that was posted on 2015. The application notes posted on 2013. Okay, so all the information that matters is either left or right. Good. So, but anyways, let's go and click on the new project. And when you start to work on a project, you always, okay, that's fine. Always also need to decide about the hardware. So this is hardware specific. At this point, you would need to know which processor you are using. There are two processors there. The difference in between those is actually the number of blocks on the on your chip. So how big designs you can make. And my preference is that it's usually on the this part. It's this 27443. Okay, let me take a see if this camera actually does anything for it. So that chip, it says CY8C27443. If you have that one in a package, still change this one. And how to change it? Basically, we would love to have a very small screwdriver here. Lift it very gently on the other end first. Yes, we need screwdrivers here. Yeah, good, excellent. So not with the hands. If you force it, then it actually usually bends the legs, and then you can bend the legs only once. Yes, there's also a tool for that, but the small screwdriver actually does the same trick. Yeah, you have that one, yes. Ooh, wow, you are well equipped with all the tools required. Oh yeah.
other thingies.
Uh-huh. Yeah. Okay. But anyways, so the chip. Chip of our choice is.
I didn't find a screwdriver, but I just got
Yeah, that'll do too. So, but anyways,
so.
chip is CY8C27443 and something blah blah blah. That's the after the dash. It is actually the package type. All right. So let's change that. Meanwhile, when you're making a project for PSoCs, my preference is usually to make the PSoC directory. Okay. Location, for example, the default location, but then PSoC projects is a good directory location. Huh? What does it do? Oh, it actually, it didn't find, couldn't find, alright, so basically what you need to do is, no, there. Where's documents? My documents, make new folder, PSoC, oops, projects. This you need to do only once in your own computer. And then, okay, name of the project. I would prefer if you actually put there your, for this course, put your own ID. For example, my login ID is anti-KP. And then, what did I tell in my instructions? How to name it. It was task 1. Like Metropolis ID. SD means the initials for this class, so it's sensors and devices. Sensor and interfaces. Okay, oh, yeah, SD. Or sensors. And then exercise 1 or E1. That'll be just fine. That way it's easier for me to even from the since I will be unzipping your files. Okay, it's easier for me to then to do the assessment. So the naming of the project. So your login ID, for example, or some ID. Or your first name. I don't care. As long as you use the same thing all over the way. Then, for example, sensors course, and then exercise 1. Okay. Before clicking yes, target device. We need to change the target device. Normally, well, if this was a new application and you more or less have a feeling that how big device you need and the packages and that kind of things, then you would go to device catalog and start finding a circuit that actually fits into your needs. For example, if I actually want to have a let's see. For example, 6 analog blocks. Oops. So those are the devices that have 6 analog blocks. Okay. And if you want to have a USB, those are the devices available for USB with the USB. So USB 2.0 the device. Okay, but we are not using them. So I'll just clear the filters. And I'll just select my chip 27443. Part number. Where's the 27? Yep, 27443. PXI. Yep, that's it. Well, the those 4 letters can be different because that's just the package. The chip is exactly the same inside of the package. For this designer, it doesn't make any difference which of the packages you select. These are the most important, since this actually defines what is inside. Okay, and you would use that 27443 because I tell you so. Good enough reason, right? That's a good reason. Actually, when I'm checking the exercises, then I also, use the code directly on my platform. Okay, so I don't want to go and, switch these devices, every time I get different kind of processor there. Okay, so then you just click OK. Another selection you can actually have here is if you want to really want to use assembly code, good luck. You can use the assembly code even if you do this. It's just a selection of which code is the main. Okay, but C is better.
It's all right if I do it in assembly.
Yeah. Yeah. Do you really want to use do assembly?
Yeah.
Okay. Remember the first rule of assembly code. Every single line must be documented. And I'll be watching where's the tabulator. Are you still sure you want that? Yeah. Yes, you can. Yes, you can. Okay. I'll just show you one how to how to create a project. There are 3 selections. We are starting now from the scratch, meaning that a new project, but you can actually clone an existing project. Okay, for example, if you start with a smaller device that you eventually need, you can clone this project and select a different target device and continue your design there. And that's basically the only way you can change the device after you have started the project. You have to clone it too and use another device. And yes, we can also start by cloning an example project. That might actually work if you are doing your self-study kind of thing. But here we start with a new project. Click. A lot of things happens. Yeah, you agree this. It has another applet to do the graphics. So the Cypress Semiconductors is actually a integrated circuit chip developer. Everything else, like these tools, they are bought from somewhere, and that as this Cypress, the PSoC Designer, they have built more or less themselves. But for example, the graphics viewing is from Adobe, that package. Okay, and the compilers, they don't have their own. They have either ImageCraft or some other compilers, but they bundled in this free tool. Okay, so that's what this chip looks inside. On the top half, there are, so these are the digital blocks, and on the left hand side those pins can be used as digital input. So these here are actually pins, port number and which pin. And on the right hand side actually is the digital output. And well, fundamentally the same pins. You can even route a signal so that it goes from output to input using a pin. Okay, then there are some switches or lines with switches, digital lines. And these actually are the vertical lines here are each bit on odd ports or each bit in or the even ports. So you can actually connect a, for example, port 0 any pin to corresponding pin in GIE, even port, or port 0 or port 2 would go into this 8, and then the port 1 can be connected to any of these. Okay, so there are some limitations. So for example, if you want to use both port 0 and port 2 as digital inputs at the same time to those blocks, you cannot, since they are using exactly the same global input line, the line. Okay, and basically right, and these lines then can be connected into, okay, by nibble. So for example, there are these raw inputs, only 4 lines to collect the raw inputs to these 4 digital blocks. So there basically you have a multiplexer you configure to whatever lines you need. So that raw input 0 can be actually row 0 input 0 can be connected to either global input even 0 or 4 or GIO 0 or 4. Okay. So those are the input rows. This is the broadcast row. So basically if you need one signal to selection of circuits, you will actually connect it using the row broadcast. So that can be connected in a broadcast sense. Okay, so that's the input part. Same for the outputs. These blue lines are each of them actually are in 1 bit on a nibble that can be then connected using that global output lines on the right hand side to those corresponding pins. Okay, it looks a little bit complicated, but you get when you get hang to it, it's actually quite flexible kind of thingy. Much less restrictions than any other microcontroller environment. So practically you can, well, it comes with the complexity, of course. If you have a chip that you have those pins and these digital blocks that you can use in universal way. Okay, it comes with the there's always the other side of the coin. Adding complexity increases complexity. Okay, great. That's my philosophy. Yeah. Okay. Then there are these feedback lines actually. So these lines are used to have internal connection from, for example, from this global out even 0 to global in even 0. So corresponding input line. Sometimes you actually need those kind of things. There are some special the configurations where you actually need them. But fortunately, most of those are already predefined configurations. You don't need to worry it otherwise than not to change anything. Okay, but anyways, you can feed back some of the digital information into corresponding lines there without using any pin. Okay, down below, analog blocks. Two kind of analog blocks. These top blocks, ACB, means actually analog continuous time block. And so basically those are traditional operational amplifier circuits with some switches for all kind of stuff around. But anyways, the operational amplifier is working continuously. Okay. But then we also have these switched blocks, AS. There was even some difference between ASC and ASD. I don't remember what was that one, but they're still both of the ASC and ASD kind of blocks are. They are both switch capacitor type blocks. Have you heard of switch capacitor technology? Okay, that's how you make a variable resistor. By using only switches and capacitors. Simple. Two switches. This is the fundamental principle. There you have a constant capacitor. Okay, this is input, that's output. Switch that one, you will get some charts going this way. Okay, and then basically open that one, close this one, you'll get the another chart depending on the voltage differences going that way. So what it actually means that the switching frequency is controlling the conductivity of this circuit, meaning it's a frequency controlled resistor, adjustable resistor by just using the switch. So that's the fundamentally why we have this kind of switch capacitor things here. So what you can do with this kind of basic structure is you can make integrator. By default, it's already integrator. Or yeah, so you can basically, since you have a capacitor, and if you have some current, it starts integrating the current and building up the voltage. Okay, simple. Then using the okay, if you have done some analog electronics, your share of it. I know that in Frankfurt they have Sallen key low pass filter. And tuning it means that basically the characteristic of this filter depend on values of those. So basically the Q factors and also then the cutoff frequencies, that kind of things, depend on the values here. Especially you well, the capacitors you can actually tune by selecting from a set of capacitors. You can always select a certain range. That can be done by just have a multiplexer for capacitors. Okay, but where you have the tuning, where you need to tune these resistors. And now this switch capacitor technology combined to that one means that you can make analog filters that you can tune. All right, and there is a tool actually to tune them. Good. So technology is there on the blocks. So there are continuous time blocks that is basically just amplifiers, that kind of things. And then there's a switch capacitors blocks that can be tuned to do some filtering or A to D conversions. Then on analog, okay, analog inputs are on the left hand side again, and as you can see, there's the number of pins are limited. So if you have a mixed signal application, you can actually, you should use port 0 for any analog input and select those first, then see what pins you still have available for digital. Okay, but for those analog pins, you can select this, oh, not that one. That 4 multiplexers. One is for the odd pins, port 01. Actually, it's a 4-bit multiplexer to select any of those odd pins 1, 3, 5, 7. The port 04 multiplexer is actually for the even pins 0, 2, 4, 8, 6. And then we also have this input select. So this left hand side, this multiplexer you can use to get 4 channels in. These 2 you can actually use to have 8 channels in, depending on the application. And yeah, then there's another set of. So this is basically just the left hand side. From the middle it's same as the right hand side. Mirror. Looks like it's mirror, more or less. Okay. But anyways, it's the a little bit different configuration of the different blocks there. But the input wise, 8-bit multiplexer and 4-bit multiplexer. Okay, because this input multiplexer can be connected only on those 3 blocks here. So column 0 analog blocks. And this can be connected to any of these the column blocks. Okay. Then actually there are some internal connections between each of those columns. You can criss and cross some of the blocks from the okay, some of the blocks here use the output to connect it on the left hand side. Okay, you can do it, but it actually might require more than one trial and error before you find the right placements for the blocks. Okay, but fortunately everything is done with the graphical tool, so there's very little room for errors. Okay, then what else do we have? All right, so we have actually these clock select lines. They are for the analog blocks on this chip. You have 2 select lines from the blocks, the digital blocks. So you can have a, for example, oscillator circuit on the digital blocks, actually counter, down counter, and use that as a clock signal to these switch blocks on each row. sometimes, for example, in here, you need to have a specific frequency to operate the clock. Then you would do the clock on digital block and connect it here. Okay, so both of these actually, either of these can be used. So basically you can have two different clock rates coming from the digital blocks. And there's total eight blocks there. And two of them can be actually then connected here. Okay, but there are also, then what is the clock that comes in each of those columns depends. Okay, so all of those columns have one single clock which is selected here, analog column clock 0, and there are 4 different places to select. Okay, wait a minute. Yeah, so you can select it actually from 2 different dividers, or either of these. So those 4 different sources. So analog clock select 0 or 1, or then the system clock. Okay, system clock divider. On the left corner, we have a winner on the left corner, somewhere there. Let's see. The global resources. Do I have the magnifier lens? No, I don't have it here. On the left hand side there are the global resources. So basically the MCU has some settings that define how it operates, and for example the CPU clock, how fast the CPU is running. Most of the chips have 24 megahertz internal clock. Some devices actually have 12, but not too many. That's one of those, you know, the datasheet informations. But anyways, CPU clock, for some reason there's a 3 megahertz default on this chip. I don't any reason why to use anything else than the system clock, but anyways, well, it's just fine. What would be the reason to run a processor on smaller clock rate? Can you less average power raise? Yeah, right.
And,
yeah, less emissions. Yeah.
building on the breadboard, you will have definitely.
Yeah. Higher frequencies may have actually some problems with you have a interconnecting with it. Yeah. For those reasons, but well, yeah. Who would? On the power consumption level, basically, how to do the low power consumption? You don't operate slow, but in sprints. As fast as possible means that you are spending very little time on doing it, and the rest of the time you should be sleeping. Yeah, that's the way to actually do the power consumption kind of thing. On the other hand, if you have faster clock rate, then you also have more power consumption at that point that might actually do some radiation that way. So lower speed can actually affect or would be better on the electromagnetic interference, but not on power consumption. It's quite opposite. Yeah. Okay. So, well, but anyways, we can leave it like that. It has also internal 32K, big K. So 2 to the power of 15. Yeah. 2 to the power of 15 hertz. Meaning that you can put such a simple 16-bit divider and to get a 1 hertz clock rate. This accuracy is not that great.
From
Yeah.
what I remember.
Yeah, yeah, you don't make a real-time clock using that one, but you can also use external clock for that 32. Yeah, and external clock which doesn't require tweaking of your code. So for debugging you would need, or developing you need, you would use your internal clock, and then for the real device you would buy that 2-cent crystal to run the real-time clock. Okay. PLL mode. Okay, you can actually tweak that 24 megahertz signal, the clock rate to 48. That's for that's phase lock loop kind of frequency doubler, if needed. I haven't found a reason for that one yet. It's actually used on these USB devices for the high speed, but I haven't used those. Okay. That's the best resource of all. Sleep timer. You can actually make quite easily the system that goes sleep using sleep timer. It wakes up the processing automatically. You just put it for sleep for a while, and then it wakes up when the sleep timer interrupts. Okay, then we have 3 different dividers, VC1. So basically that gives the frequency of VC1, which is okay, which can be used as one of the clock sources here. Okay, VC1 or 2. So VC1 signal is actually system clock divided by the number, what is told there. So currently it's VC1 divider is 16. VC2 then has an input from VC1, so it's another divider. So 16, number 16, so it's 5-bit. 4 bits is 8, right? I can't calculate anymore. 60 values. It's 4-bit. Okay. Yeah. Yes. It is. Yes, it is. Yeah. Okay. Yeah. Correct. So 2 4-bit dividers. VC1 and VC2. Then VC3 is yet another, but that's 8-bit divider. And basically for the VC3 you can select even the input, so it doesn't need to be on the same divider chain, but you can use the system clock directly. You can actually, if you enable this that PLL mode, then you can have the system clock times 2. So 24 megahertz device, you can tweak the 48 megahertz signal here and divide it, for example, by 3, which you cannot otherwise do. Also some other odd number. Or have a very slow that would be a 4 plus 4 plus 8 is 16 16 the bit divider if you put those in cascade. Okay, but anyways, those are the general clock signals that you can use most of the places. So the sleep timer, it has its own settings, 4 different settings. So it's 1 hertz, so waking up once in a second or 8 times a second or so. And these VC dividers are actually then used for various kind of applications. It means that you don't need to use digital blocks to do the clock division. You can use these. Okay, and system clock source can be internal or external. It has the tuned drivers to drive these crystals directly. Okay, and system called disable, no disabling. Okay. These analog things down below, don't worry about those yet. We will go through those on when we are going through this analog A to D conversions. Since those are basically defining the span and where the reference level is for the analog circuits. This is unipolar system. You cannot put negative voltages as input signals, meaning that you can only have the positive biased signals. And the analog circuits are designed for bipolar signals, so how you make basically dual-sided power supply. The way that you do it, you define plus V here and minus V here. Both are positive, and then you have the virtual reference ground somewhere. And those are the settings for the analog parts. Okay, good. So, yes. What we have here, pin out. Okay, there you can actually, on the left corner, that's one place to start defining pins, how they are connected to the next point, what kind of drive, if they are outputs, what kind of drive they have. Each of those pins actually may have 8 different driving modes. By default, those are in high Z analog. Was it high Z analog? Yes, high Z or high Z analog mode. High Z and high Z analog fundamentally they don't differ much from each other. Yeah, but anyways, so high Z means that it would be used as an input. High impedance mode. Then there are modes like open drain high, meaning or is it high side is strong, and then the low side, so you can was it that way? Open drain. Okay, yes, it must be like that, so that it's either connected to high or left open. So meaning transistor on high end. That's plus voltage, and then it can connect basically it can give current to the device or pin, but it actually or actually it can be used to connect plus the power supply to a pin. Otherwise it's floating. It's either high drive on the operating voltage or high impedance. Open drain low is the opposite, so basically you have a transistor only to pull the line down. So you can that one connects the signal to the ground or left it floating. Pull down actually means a pull down resistor, and pull up means pull up resistor. Quite simple. For example, where you can use these is if you on as an input. Okay. If you have a push button, for example, on your circuit, and high side push button plus 5 volts, and you want to use that one to connect to some circuit, you need a resistor here to pull it down. In this kind of cases, you don't need the external resistor. You can do the pull down resistor. So that one actually keeps the signal on ground unless there's a voltage coming in. Okay. Pull up and pull down. So those are used for the input. This is especially for the digital input. Or, okay, if this was a I2C device, basically you can do low speed I2C without external components by making it as a pull up, and then tweaking a little bit with the more code while you're actually driving the line. But anyways, it can be done. Then there are two modes of strong meaning a totem pole. So there is a transistor on both high end and low end. That's the most typical for output signal. Then it can actually drive anything. Strong, slow means that it gives more power, but the rising edge and falling edge are slower. It has, well, it doesn't generate that much transients. Okay, good. So those are the inputs, input drives. Okay, then any of the pins can be used as interrupt source. Yoo-hoo! Any pin will generate one single interrupt, meaning that on the interrupt service routine you must check if you have more than one pin interrupting, you need to check which pin was the active one. But anyways, it's just, you know, it's quite universal. Which is good thing, right? It's also the, you know, the how to start a never-ending project. Just make it universal. Oh boy. Okay, all right, let's do something here other than just making jokes. Let me then, so this is just how the chip is organized inside. Yes, there are some modules, programmable blocks, there are some lines, so the interfaces, there are switches, how to make any devices. Well, that's where the lower right corner, user modules. That's the key to any design. User modules. Let's open, for example, that generic, not generic. Miscellaneous digital. Okay, MISC digital. These are, you will most probably need some of those blocks at some point. This miscellaneous digital blocks here actually are something like, okay, let's just for fun, let's put there a sleep timer. So usually we need some sort of simple timing logic in our code. If we add a sleep timer, what it actually did is it added this sleep timer block into our design. So inside of the loadable configurations, there's this user module now called sleep timer 1. Okay, and on opposite side the sleep timer settings. Okay, so for example, I can rename my sleep timer, and then the only parameter what I can fill here is the what is the size. So basically this is the divider size, and I don't any reason to use any less than 4 bytes. It doesn't make the code any longer practically if you use that 4-byte divider, since basically this divider actually is a software divider. So what is the biggest count you can put there on the sleep timer that it would sleep? The biggest number, 4 bytes, so that would be big enough. So it's 32-bit. Yeah, big enough for most of the applications. The real divider, sleep time divider, is actually one of these global resources. For example, there you can select 64 Hertz. Okay. Now I have a sleep timer on my design. How to use the sleep timer? Well, the next step after you have added anything on the design, you actually go and click not generate build, but the generate configuration files. Okay, so the workflow here is you will add the components or modules from the existing ones in this C. This is a chip level design. Then click the configuration files, and with that click actually we got something more. Okay, so now the workplace explorer here, we can go and see, okay, we have actually main.c, or you have the main.asm, right? Assembly file. Also it has the boot.asm. So what does the this system actually do, or the development environment? Basically it makes the pre-generated code to boot the system and call the main.c. Okay, so it's always basically the code starts from the boot section, which is nice since you have done some assembly programming, and every single assembly program starts by initializing the processor, the environment. You have to put the code there to basically select some clocks, rates, and fundamentally the left hand side corner, whatever you select on that global resources, that will actually end up being a code in your boot.asm. Okay, and then when you build the project, basically it makes this downloadable hex code that you can program the chip basically to run the boot code first and then call the main function. Okay, so if you ever thought about why in the earth in C programming we call even the main program as function, it is a function. Okay, anyways, what else that clicking actually did? It also gave a selection of library source files and corresponding header files. They are, and those are assembly code. Yeah. So all the software libraries here are actually when you are putting any of those user module there, it will actually translate into some assembly code which is named after whatever the name on that block is. So if I change that sleep timer name to food timer and click the generate configuration files, now I have the block name is food timer and the corresponding library assembly files are food timer.asm. Okay, so it's code generation and the code is generated at assembly level. Okay, most of the time we don't need to actually worry about that. Moi, tuu sisään, täällä on kivaa. Okay, so most of the time the you don't need to touch the assembly code, but yes, you actually sometimes you do need. Okay, so food timer, and then basically now you can actually go to your main C routine and start calling those functions. Whatever functions you put there, all the modules already are, the header files are already inside of that one, PSoC API.h. So those function prototype, which is quite important on C programming, that you have also introduced a prototype of the function before using it. Those are already there. So all what you need to do is actually write the user code on that place where it tells. So what did I tell you about the minimum requirement of documentation? This is exercise 1, sensors and interfaces, and then put your name as author. Or if you are doing this, you can do also this on pairs or small groups, as long as everyone learns. And then date. So this is then, after these markings, it's your property. Your intellectual property. That's how you claim them. Okay, then anything what you include here will be actually executed eventually. All right, so actually I added a food timer, or that's a sleep timer with the name food timer here. Oops, I didn't want to go there. You can have a nice data sheet of that one. This actually is the full data sheet what that function is doing. Okay. And with the application programming interface, and also what I like the best is example code, sample code. So sharing is caring, so that's nice that they have actually shared some of the code that say 99% of those sample codes are actually working. But not all. Seriously, there's some maybe unintentional mishaps. Anyways, one way of working here would be just to copy and paste the sample code here. There you go. Okay, So that would be just testing, and so I would guess that after this one we would have about 8 hertz rate in our operating system, meaning that while one loop forever. So what this one actually does now, since sleep timer is based on interrupts, you must actually enable the global interrupts before anything happens. Okay, then as with the any module, you have to start the module, configure your module, and if there's an interrupt based module, then you have to enable it. Yeah, and then just use the functions what the user interface does. The fundamental problem with copying and pasting is that you should also think what you are doing. Now, how many of you can see why this wouldn't even compile? You see it?
I don't have my glasses on.
Oh, okay. You are not watching. Okay, what is the problem? Fundamental problem here.
Different clock, right?
Hmm?
Different clock, right?
No,
There is no return.
no. More obvious. It comes with a syntax error.
Yeah, like this, because in the second line,
No,
another line 9.
that's our module name. Full timer module name, and we are calling sleep timer. We don't have sleep timer, we have full timer. Now you remember it. That's the most common error what you make when basically you are taking the sample code. Yeah, so everything actually is named after that module. It's always start with that module name, and then there's the whatever it does. Okay, and these samples are always done for the default, not even the default actually. The default for the sleep timer was sleep timer 1. Okay, so you need to either change the name of it on the chip design or calling the correct correct function. Okay, so that's it, and now it would run, although this is a little bit dumb since, well, we cannot actually see it running. Right, okay, but let's in any case click the my favorite button, generate and build. So generate and build does the generating of these interface functions and the code, and then it compiles all the files, and then it links the files, and it also from the linked file it generates the downloadable code to the platform. So this came out with no errors. No, 3 errors, only 3. Undeclared. Of course, yes, that was my fault. See, all names, also those names will change. Not sleep timer, but full timer. So everything is named after that one. Let me click it again. Build. Now it should work. Full timer, full timer, full timer. Yes, 0 errors, 0 warnings. Okay, then next step would be actually to this box didn't have any USB. That's funny. It didn't have any. Yeah, better. USB cord was missing. and then I have. Oh, this is a correct chip. Excellent. So, but this one does. Oh, yes, it does. I should always buy just new ones. Annual donations. All right. So, the next step, since we have a functional code that we can only test that it actually downloads the platform. Let's do it just for fun. All right. That goes to the USB port. There is a chance that you need to actually update this program import when you are taking it out of the box. It's very simple, but the programmer actually the software prompts for, do you want to install a new code or the firmware for this one. This is also a PSoC device inside of this programmer. Anyhow, so at least my computer here says mini programmer 3.4.1.20 device driver software installed successfully, and there's a 5-pin connector, and you cannot connect this the wrong way, even if you try, even with force. Or should I try? Yeah. And if you do, nothing bad happens actually. It has been designed such that you cannot make a real damage by plugging it the wrong way. As long as the pins are aligned, then will be fine. Okay, so next step would be to program the device. So program path. Okay. There are different ways to program. In here, we probably want to have the reset mode. That's actually a little bit faster way of programming. But then we also need to turn the power on. So toggle power. When you have power on, the red light comes on this programmer pod. Okay. And then press that one. It takes few seconds to program. Okay, now it's done, and my program is running. Great. Nothing happens. Well, sleep timer is actually, it is running on a loop with 8 Hz doing nothing. Good. Yeah. Okay. Anyways, now we have managed to program it. If you had the wrong device there, then it would actually not work at all. So it doesn't start programming unless it finds the right device on the other end. Okay, but today you also need to make the LED there. That's simple. The same way as earlier. We include LED. Just double clicking the LED module here. Okay. Clicking it here, actually it then we can change the name. Okay, but maybe I will call it Blinky. Blinky. Okay, we call it Blinky. Now we can select the port pin and drive. Okay. So this chip has 3 8-bit ports, and this board has 4 LEDs. So by some wire you should actually be able to connect one of those pins to one of those LEDs. I will use just for fun, let's see, port 1.5 for example. That's fine. You have your instructions on the exercise sheet. Read the instructions where you should go. I just put it somewhere. My selection is port 1, pin, what did I say? Pin 5. So setting on this one must correspond to the pin what you are using, and of course how the LED is connected. And these LEDs are connected actually. So that's your port X, Y, and then basically there's a connector. Then there are these LEDs with current limiting resistor down to ground, meaning that basically this drive active load does not work. Active low meaning you can draw it down to ground, not push any signal up. So we changed that one to active high. And yes, you can overwrite any of these parameters or so from the pin output driving mode. Or by software later on. All the pin settings and that kind of things, all settings shown in this picture are software configurable. So these modules just give you easy access to the physical thing is what there is inside of the device, but it's this code that tells what to do, so you can overwrite everything by your own code. Okay, so port 1 pin 1.5 is now there, named Blinky. I will generate the configuration files, look at the main.c, and we can put basically the Blinky, and datasheet window already have that one there. Let me see, I probably want to also include some of the Blinky code here. Blinky start. First command is always the start the device, no, almost always. Then basically we can turn this Blinky on, switch on, and then inside of the loop Blinky invert. That's a function. So that flashes. And now the flashing rate is how many flashes a second? If I have it inside of that forever loop. Our forever loop actually runs on 8 times a second. How many times LED blinks? We'll see. Yes, half of it. Yeah, of course. It turns on, and next time it turns off, on, off. And blink means on, off. Yeah. Otherwise, it doesn't blink. All right, and then let's spray and see if this one compiles. No errors, no warnings. I can then program the path. Power is on now. Program the code, and hopefully this one blinks the LED. Still program. Done. Ooh. Blinking LED light. I must show this one to the world. Okay, blinking LED light. All right, so that's the LED is the easiest way of putting anything, any I/O action. If you want to drive a transistor, for example, you just put an LED module there to drive a signal to some pin, and then you have the external transistor. Okay. Just like in my infamous electronic lore, there's only one driving transistor for that motor. The motor takes about 200 milliamps of current when you run it, that vibrator motor, and basically you need a transistor to run it. Yeah. Okay, good. So, blinking light. On the today's exercise, or this week's exercise, so basically be done with the exercise by the same time next week. So that's the deadline, 1 week. Pin input is a little bit more, it's not really complicated. It's just different. Since practically we already have all what we need on these this file here. Let's see, was it the config? Yeah. So all what you need to know is already on that PSoC GPIO.h. It's already there. But how to find the right place, well, that's another question. So for that reason, we actually go and first make sure that our input pin actually functions well with our external devices. On this board here, there's a switch button. There's also the reset button actually, but on the lower corner, oh yes, it's the lower corner, lower right corner, there's a switch button and input for it. This one actually is connected to +5 volts. Okay, so that is our switch 1. In order that one to work, you need a pull down resistor that keeps it on 0 until you press a button when it gives the high input. So basically for the input you need to make this one of the pins, the input pin, actually a pull down mode. Or you can add a resistor, external resistor to the circuitry. But anyways, you need that one. This one itself, it doesn't work. It's just a connector. It's just wire. Okay, so how to make that one? Let's go back to the chip design. Just for fun, I will take one of those ports, for example, hey, port 1, pin 7. I can rename that port on the lower corner, call it button, just for fun. So that's the button. And that would be, type is pull down. In this exercise, we are not yet using the interrupt, so that's all the things we need to do. So we have a button with a pull down the drive, and if we just click the generate configuration files, what it did, it actually it added some code on this PSoC GPIO.int.h, the header files, which now actually have well, there's a blinky. Those are the real settings for which pin in which port are for the blinking LED. It also have the drive modes and that kind of things. Don't touch those. Okay, and actually don't even touch the blinky pin settings here. What you actually would need is here the blinky pin mask and then button data ADDR. And you don't actually, oh, not blinky. You need button mask, not blinky pin. Button mask and the button data ADDR. So button data adder actually points directly to the port where your data is. It's 8-bit data. So it also shows every other pin on that port. You would need to use the mask to actually select only the pin what you are interested in. And there you need a little bit of, say, fancier operation, bitwise operations, bitwise masking. But that's extremely simple thing. Let's go to the main routine, and for example, I could put here, since we don't add any modules, but we just defined a pin, we don't need to put any starts or stops. We can directly start using the code basically by saying if button data adder. Okay, bitwise AND. What is bitwise AND in C? Yeah, it's AND. Single AND. Double AND, it's logic. Logic AND, but this is bitwise AND. Big difference in between. Huge difference. Logical AND is or logical in logical operations. Basically, the only operation here is if the false is 0, true is anything else. Okay. So if you make the double AND here, then would have comparing the logical true to anything else. So if any of the bits on the other on that port would be high, then would give false answer. Okay. Then bitwise AND to AND with mask, button mask. Okay. So basically, that's just an example code. Well, now I should get blinking only if I press that button, or if that line is up and I used which line I used actually 1.7. Okay. Like that. So yeah, that's actually how you read the input data. You need that AND operation, mask, and the basically the variable where your data is. Okay, so couple of warnings. If you are driving a line, if it's an output line, and you would like to see the state of that output line, then this is not the right way to do the checking if the output line is 1 or 0. Because if you are driving a line, it always has a load. And basically what this one does, the input, as an input, the pin basically just checks if the voltage is higher or lower than I think 1 point some volts practically, but anyways, above 2 volts it's 1, and above below 0.8 volts the state is 0. Okay, so if you are driving a for example, directly some LED that might drop the output line lower than the level, although you are driving it. But if you are reading the same thing, you will get a false logical state. Okay, I have seen that happening so many times, so I have to just warn you about it. I have done it myself once. I learned it from there. That was when I was very young. Okay. Good. Yeah, so I have the timer. Timer. I have the button. I have LED. I have no errors, no warnings. I can program the path. And start wondering why it doesn't work as I want. Hey, it might actually work. It's that LED light, and it's now not blinking, but it's shining. So basically it's here. Blink is switch 1. So it actually, that's the state, and this one is probably running still at 8 Hertz. But I haven't pressed the button. If I press the button, oh, it's blinking. And if I stop, it stops blinking. Yeah. Yeah, it works. Good. So basically that concludes my today's lab tutorial. We went through quite a lot of those, bits and pieces, how the system works, and then a little bit of this, how to make the code. So let's review it quite just briefly. Mask. Okay, yeah. So basically, this variable here, button data ADDR, is pointing into I/O port register directly. So that variable actually holds the value what is shown as for the port. Yeah, logical values, meaning high is more than 2 volts, low is below 0.8 volts, TTL levels. Okay, but this port is 8 bits. So it shows the whole, every single bit there represents 1 pin. And basically, this mask is just the defined value to use to basically mask that 1 pin. So if you then use the bitwise, and then it basically masks those other port pins down, forces those down, and then what is remaining is just that 1 bit. Yeah. And yeah, in main.c, so if that is true, meaning non-zero, then it basically just does the blink invert. Yeah. All right. So then again the review. So you will do it or start the project usually by starting from scratch, meaning a new project. Select the device accordingly. On this course you would use the this 27443. On the real life you need to basically find the device that matches your application. Okay, there are plenty of different devices. Then you do the basically the system level design on the chip level using user modules. You just add the corresponding modules. I didn't go through all of those. Well, there are plenty of different kind of things here. We used only today 3 of the 2 of those MISC digital kind of logic, but there are A to D converters, there are amplifiers, there are analog communication devices like dual tone multiple frequency can be found here. counters, different kind of digital counters, D to A converter, and then a selection of digital communication blocks, and so on and so on. So huge amount of user modules for you to use. Just, include those to your design, set some parameters. Today we don't have any blocks used yet for a reason. And then basically generate the configuration files, and configuration files here mean fundamentally this main.c or main.asm, and then these library source files and library header files. So those are automatically generated to match your modules you used on this one. And then on main function, you always start by initializing the system, meaning you'll call the routines to start different user modules, put the configurations, and then you have your own main code, whatever you need to do. So that's basically how you make the code to work. And then after some hours of documenting, that's not the right date. Okay. After hours of documenting, you would test it. So basically, generate build goes and okay, that complains about that file which is open, and basically the build should be clean build, meaning that no errors, no warnings. Errors you cannot go forward, you have to just fix them. Most of the errors comes from the the naming kind of things, not real other errors. You cannot see the errors you have done on the parameterization. Those are your own errors, but this checks the code integrity and that kind of things, and links and blah blah blah, makes the programmable file, and then you have this program path facility to download it to the chip and test it. And yes, of course, you need to at some point do the you need to also do the wiring. One thing I didn't show you, I think you can work it out yourself, is the LCD. You will just add the LCD module, and basically after adding the LCD module, you do those little things and read that data sheet.
I can see that we have to return the main C in the report. And what was the other thing we have to report?
That's just a moment. Yeah, this one. Okay, I'll show you. Okay, this one actually copy paste. Let's see. Copy paste that one somewhere on your Google Drive and make a Google Doc. Name it accordingly. Example, exercise 1 main.c. Oops. Okay. Main.c, and then paste. And okay, with that one, you also need to share it. Okay, this is the company kind of thingy. So, wait a minute. Where's the for commenting? And let's see. Why doesn't? Oh, I see. It's not full. Yep. Commenting. Okay. So if you are actually using Metropolia Google account, then that's just fine. just for Metropolia account can actually then comment. Or actually, if you are using your own personal account, then you click allow external, and this is the link you want to share. Okay, share it by the rules. You know. Okay.
And what is the other part we have to also send you that the other second, the first link?
Okay, the first link is the project files. So go and find your own project wherever you put it, zip it, and then upload to your favorite cloud service. And if it opens, then it's fine. I think the Dropbox is the best one there, since you don't need to care about the sharing properties. It's yeah, or Google Drive. One way actually do a sharing quite easy to make a Google Drive or one directory on Google Drive so that it's the whole directory is saved, shared. So then you can, whatever you put there will be automatically, you know, the settings are there, and that's one way. Yeah, or Dropbox. Yeah, you can do the same thing. It's up to you what you decide. But those are the things. So don't. Okay, every year I also get the links to C colon. Okay. Seriously. Well, probably not with users. There's so little number of students, but there's some links actually starting with C. Well, for some reason they don't open correctly. Yeah, why don't can it use us? Okay, sure. You don't want me to do that. Well, I cannot actually do that, but Kimmo Sauren, he's actually teaching practical attack and defense, so don't send them that kind of links to him. Okay. Good. Anyways, so that's my part of the show. Now it's your time to do the exercise based on the exercise template, which tells you what to do. Any questions?
So the thing we have to have it in starts with task 2, the LED. Task 1 is follow the leader.
Yeah. You just follow the links. That's the whole thing. Return the links.
Yeah, the task in the task key.
Yes, task. Yeah. So let's go through that exercise. What you need to do. Okay, read these things. So basically, you have an LED. Unfortunately, now it's on the wrong pot and pin. For example, and then the sleep timer initialization. We have 64 hertz. On this design, it's of 64 hertz. Yeah, full timer 64 hertz. Then, required connections, meaning the right port to the right pin, and then 1 hertz blinking rate. Okay, so you need to do some, changes to the code anyway. So not too much, but anyways. And then the pin input you already have, and basically it might be on the wrong place now, I have a feeling. Okay. Then modify the, LCD display I didn't show you, but you know the drill. You add the LCD. One small hint, I think it does not say it anywhere, but except, let's see, did I say it here? Yeah. So this board actually uses port 2 for the LCD output. And then you need to do some modification of the code, of course. It's also some reading, meaning this basically just means the reading of the what is the LCD? digital LCD display. Okay, reading the datasheet for LCD display. Okay, and those things in one project, C main file or assembly main file in your case, so that I can comment, link to that kind of thing, and then compress the project folder, move it somewhere on the cloud. That's the another link, and then you are done. And deadline is next Wednesday 9 o'clock, so you should be done before the entering the next one. Good. Thank you for your attention. Welcome back next week.